Please relax your body and find a truly comfortable position on your soft bed. Let your breath slow down, becoming as steady and gentle as the rhythm of the ocean waves at night. Outside, the sky has draped itself in a silent curtain of darkness, and high above, millions of tiny specks of light are twinkling like the storytelling eyes of the universe. Have you ever wondered, as you look up at those stars, millions of light years away, how we can possibly know what they're made of? How do we know that in those distant places there is iron, or gold, or torrents of hot hydrogen gas, when not a single human, not a single spaceship has ever been able to touch them? Tonight, we will begin a journey to find the answer to that very miracle. Imagine you are standing in a vast, grassy field on a moonless night. The space around you is dark, with only a cool, fresh breeze brushing against your skin and the gentle scent of the earth. When you lift your eyes, the Milky Way appears like a faint, shimmering ribbon of silk stretched across the sky. The stars you are looking at are not just lifeless specks of light. Each star is a brilliant sun, a gigantic ball of fire burning brightly in the vast emptiness. Some stars are very close, but others are at a distance so great that our minds can hardly comprehend it. Distance in the universe is something both terrifying and poetic. When we say a star is 1 million light years away, it means that the light from it has had to travel through space for an entire million years to reach your eyes. 1 million years is an incredibly long time, longer than the entire history of modern humanity. The light you see tonight is actually the past of that star. You are looking through time, touching the memories of the universe. But even from so far away, that light carries with it incredibly precious information. It's like a letter sent from a distant friend, and our task is to learn how to read the language of that letter. In our daily lives, if we want to know what something is made of, we usually touch it, smell it, or take it to a laboratory for analysis. But with the stars, we can't do that. The closest star to Earth is the Sun, and it's about 150 million kilometers away. If you were to travel on a modern jet, it would take you 19 years to get there. As for the stars in other galaxies, millions of light years away, sending a ship there and back is impossible with our current technology, and will remain so for the foreseeable future. And yet, scientists, those sky lovers with patient perseverance, have found a brilliant method. They don't need to go anywhere. They just need to stand right here, on this small blue planet, and listen to what the light has to say. Light is the only messenger connecting us to the rest of the universe. It travels through the thick, dark night, crosses the empty voids between galaxies, and carries with it the codes of the chemical composition, the temperature, and even the age of the star where it was born. To understand this, imagine light as a clear stream. At a glance, the stream appears pure and simple. But if you place a prism in its path, the stream will fan out into a myriad of brilliant colors: red, orange, yellow, green, blue, indigo, violet. That is a rainbow, a symphony of color. But even more miraculously, if you look very closely at that band of color with sophisticated instruments, you will see tiny black lines, as thin as a strand of hair, appearing in specific positions. Those black lines are the letters in the alphabet of the universe. Each chemical element, whether it's light hydrogen, sturdy iron, or precious gold, leaves its own distinct marks in the light. They are like unique fingerprints. When light from a star passes through its own atmosphere to shine into space, the elements there will absorb a little bit of light at very specific colors. The job of astronomers is to capture that light, split it apart, and look for these lines. If they see the lines in the position for iron, they know for certain that the star contains iron. If they see the traces of hydrogen, they know that the star is burning with the most primordial source of energy. Take a deep breath and feel this miracle. You don't need to touch a star to know if it's warm or cold, to know if it's old or young. Just a tiny ray of light falling into the lens of a telescope, like the Hubble telescope or the James Webb telescope orbiting in space, is enough to open up a treasure trove of knowledge. In the next chapters of this story, we will learn more about the people who first discovered this secret. We will meet those who dedicated their entire lives to observing faint colored lines, and from them mapped out the entire universe. You will see that, as it turns out, we and those distant stars have a much closer connection than we thought. The elements that make up your body, from the calcium in your bones to the iron in your blood, were all forged inside a star that died billions of years ago. Now, let your mind float among the stars. Imagine you are gliding on tiny particles of light, tireless photons, streaking across the vastness of space to bring news back home. The space out there may be cold and empty, but it is always filled with warm messages from the light. Do you hear it? It's the whisper of the universe. It's telling us that nothing is too far away to be understood, that no mystery is unsolvable if we know how to observe with our hearts and minds. Those stars, millions of light years away, are no longer anonymous points of light. They are storytellers, and we are their attentive listeners under this peaceful night sky. Sleep well, because even as you close your eyes, the light from distant galaxies continues its persistent journey to Earth, waiting for tomorrow when you wake up so we can decipher the next secret messages together. The universe is vast, yet it is also intimate, like a gentle embrace from the darkness that surrounds you now. We have closed the first chapter, a gentle greeting to the night sky. In the next chapter, we will learn more about our messenger, light, to see how those tiny particles can carry so much information across a journey of billions upon billions of kilometers. But for now, let your dreams wander among the vibrantly colored galaxies. Chapter 2. Light, the messenger of the universe. Imagine you are lying on a soft patch of grass on a clear night. The space around you is quiet, with only the sparse chirping of crickets and the scent of dew-kissed plants. As you look up at the twinkling stars, have you ever asked yourself, what has that light gone through to reach me? In this chapter, we will learn about light, the most dedicated and swift messenger of the universe, the only entity that allows us to touch the secrets of distant stars. Light is a magical thing, whose presence we sometimes forget because it is so familiar. But in the world of astronomy, light is everything. Without light, the universe would forever be a dark and silent curtain to us. Light not only helps us see things, but it is also a massive flow of information, carrying barcodes about the origin and nature of everything it passes through. To understand this messenger, we must first talk about its speed. Light moves so fast that it's difficult for our imagination to keep up. In 1 second, in just the blink of an eye, light can travel a distance of about 300,000 kilometers. To help you visualize, if light could race around the Earth at the equator, it would circle it more than 7.5 times in a single second. The distance from the Moon to our Earth is about 384,400 kilometers, and it takes light a mere 1.3 seconds to cross that distance. It is because of this incredible speed that light turns the universe into a giant time machine. When you look at the Moon, you are seeing the Moon of 1.3 seconds ago. When you look at the Sun, you are seeing it as it was 8 minutes and 20 seconds ago. That's because light needs exactly that much time to travel from the Sun's surface across 150 million kilometers of space to reach your eyes. And when we look at a star that is 1 million light years away, we are actually seeing an image that is 1 million years old. The messenger, light, began its journey at a time when we humans had not yet even formed our first civilizations. But what is light? For centuries, the greatest minds of humanity have debated this. At one time, they thought light was made of tiny particles, shot out like arrows. At another time, they believed light was a ripple-like wave, similar to the circles of water that spread out when you toss a pebble into a calm lake. Today, we know that light has a fascinating dual nature. It is both a particle and a wave. Scientists call these particles of light photons. Imagine each star as a giant nest, constantly launching trillions upon trillions of tiny photons into space. These photons have no mass. They are weightless, yet carry energy within them. And most importantly, they carry the memory of where they were born. When a particle of light is created in the fiery heart of a star, it can take thousands of years to weave its way through the star's dense layers of matter before escaping into the emptiness of space. Along that journey, it collides, interacts with, and records the composition of the elements it encounters. Take a deep breath and imagine the lonely yet resilient journey of a particle of light. After escaping the surface of its parent star, it plunges into the darkness of interstellar space. It passes through giant dust clouds, traverses regions of space chilled to nearly absolute zero. It never stops, never tires. It carries a letter written in the language of energy and color. When this messenger arrives at Earth, it brings a message about temperature. Particles of light from the hottest stars vibrate extremely fast, carry more energy, and often appear green or blue. Meanwhile, older, cooler stars send out light particles that vibrate more slowly, carrying a somber, red hue. Just by looking at the color of the light, we have begun to read the first lines of the universe's letter. However, the light that the human eye can see, what we call visible light, is actually just a very small part of a much larger band, known as the electromagnetic spectrum. The universe also sends us other invisible messengers, such as infrared rays, ultraviolet rays, X-rays, or radio waves. Each type of messenger tells a different story. For example, infrared telescopes can see through thick dust clouds to observe newborn stars forming inside, something ordinary light cannot do. Organizations like NASA or ESA have launched modern telescopes into space to capture these messengers as completely as possible, because Earth's atmosphere can sometimes blur or block some of this precious information. The Hubble Space Telescope, for over 30 years, has received light from the most distant galaxies, helping us understand that the universe is much larger than we ever imagined. Or most recently, the James Webb Space Telescope, with its extremely sensitive heat-detecting capabilities, is helping us look back to the moments just after the Big Bang, the time when the very first particles of light began their journey. Now, relax your hands and feel a sense of lightness spreading through your body. The light from the stars above is still silently falling, touching your skin, touching your hair. Although we don't feel their weight, with each passing moment, we are bathing in the stream of information from the entire history of the universe. The messenger of light is truly faithful. Even if the journey is millions upon millions of kilometers long, even if millions of years pass, the message it carries remains strangely intact. The color bands, the vibrational frequencies are still there, waiting for human eyes and minds to decode them. In the next chapter, we will learn about a miraculous tool that humans have created to dissect light, helping us see what is hidden within its pure white appearance. We will discover together how a simple glass prism can become the key that opens the door to the heart of the stars. But for now, let your mind rest. Imagine yourself floating adrift with the photons in the vast, peaceful, zero-gravity space. You don't need to hurry, because the light took millions of years to get here. It will wait patiently for you until morning. The universe is still whispering stories in your ear about our origins, about the vastness and the wordless beauty of light. Fall into a deep, peaceful sleep within the protective embrace of the night and the guidance of light rays from the distant past. Chapter 3. The Magic of the Rainbow. Imagine you are standing under a small porch after a summer shower. The atmosphere is now so fresh, carrying the smell of damp earth and the pungent scent of grass and flowers. Suddenly, golden sunbeams pierce through the gray clouds, and on the opposite side, a brilliant rainbow appears, curving gracefully against the deep blue sky. You gaze at it with pure admiration, feeling the gentle beauty of the 7 successive shades of color. The rainbow is not just a beautiful natural phenomenon. It is the very first key, the most primitive step in helping us understand the language of the universe. For a very long time, we humans believed that the white light from the sun was the purest, simplest, and most unadulterated form of light. It was thought that the colors of the rainbow were just a strange illusion created by raindrops encountering sunlight. But in the year 1666, a young man named Isaac Newton conducted an experiment that completely changed the way we see the world. At that time, to avoid a raging epidemic, Newton was self-isolating at his home in the English countryside. In a quiet, dark room, he left only a tiny slit in a window shutter to let a slender sunbeam enter. When that white beam of light passed through a triangular block of glass we call a prism, something magical happened. On the other side of the prism, instead of a single dull spot of white light, a brilliant band of colors appeared on the wall: red, orange, yellow, green, blue, indigo, and violet. Newton called this band of colors a spectrum, a Latin word meaning image or apparition. And to be certain that the prism itself wasn't creating the colors, but that the colors were already present in the light, he took one more step. He placed a second prism, inverted, to catch that rainbow band. Amazingly, all the colors converged, blended back together, and returned to a single beam of pure white light, just as it was before. Imagine white light as a group of close friends, holding hands tightly and running together on a flat road. Each friend represents a color. The red friend takes long, leisurely strides, while the violet friend takes very quick, hurried steps. As they run on the clear, open road of air, they move together in unison, creating a white appearance. But when they hit the glass surface of the prism, like running into a patch of soft sand, everything changes. Because each color has a different frequency and energy, they are bent at different angles as they pass through the glass. The red friend is least affected, deviating only slightly from its path, but the violet friend, with its high energy and rapid frequency, is bent a great deal. As a result, the once tightly knit group of friends is separated, revealing all of their distinct personalities on the spectrum. This experiment by Newton laid the foundation for the entire field of cosmology that followed. It taught us that light is not a single, uniform entity, but a collection of countless different energy bands. When we look at the light from a star millions of kilometers away, we are not just seeing a single point of light, but a treasure trove of colors waiting to be unlocked. Breathe slowly. Now, imagine that spectrum as a giant harp of the universe. Each color is a string, and each string has a different pitch. The warm red, with its long wavelength, is like the low, deep bass notes. The brilliant violet, with its short wavelength, is like the high, soaring treble notes. When a star shines, it is playing an instrumental piece with light, and each element within it plucks specific strings. The rainbow you see after the rain is the result of millions, even billions, of tiny raindrops acting as natural prisms. Sunlight enters a raindrop, is bent, reflected, and dispersed, then travels back to your eye. Every time you see a rainbow, remember that it is a gentle reminder from nature of the complex and beautiful essence of light. But the story of the spectrum doesn't just end with the 7 colors we can see with the naked eye. Newton had only opened the first door. Beyond that brilliant rainbow, there are invisible regions of color that the human eye cannot perceive, but that modern instruments can now detect. However, whether the colors are visible or invisible, they all obey the same laws of bending and vibration. Now, Let your thoughts drift along these gentle bands of color. Imagine you are lying on a fluffy cloud, surrounded by winding rivers of color: red, warm like the breath of the earth; green, cool like the forest canopy; and blue, deep like the heart of the ocean. You don't need to try to analyze or remember anything. Just feel that, even in something that seems as simple as white light, there lies a world of incredible diversity and richness. We've learned how to split light, much like turning the pages of a book. But within that book of colors, there are mysterious lines written in tiny black strokes. These aren't smudges or mistakes, but rather the most important messages the universe has to offer. In the next chapter, we will explore these mysterious black lines, the very clues that allowed humanity to truly read the chemical composition of stars millions of light years away. Let your eyes close naturally. Feel the relaxation spread from the crown of your head down to the tips of your toes. The universe is vast, but it is also orderly and logical. The laws of physics that Newton discovered in his small, dark room are the very same laws that govern the most distant galaxies. You and the stars share a common language of light and color. Chapter 4. The Mysterious Black Lines. We have marveled together at the brilliant beauty of the rainbow that Sir Isaac Newton discovered in his dark room. It was a continuous, smooth band of color, where red gracefully shifted to orange, then yellow, green, all the way to a dreamy purple. However, if the story had ended with that vibrant spectrum, we might never have known what a star millions of light years away is made of. The real magic lies not in the colors that are present, but in the tiny gaps, the silent black lines interspersed within that band of color. The story of these black lines begins around the year 1802, when an English scientist named William Hyde Wollaston noticed that the solar spectrum was not as perfectly continuous as people had thought. He saw a few faint black lines dividing the band of color, but at the time, he simply thought they were the natural boundaries between the different colors. It wasn't until more than 10 years later, in 1814, that a talented German glassmaker named Joseph von Fraunhofer truly opened the door to this secret. Fraunhofer was not an astronomer initially. He was an expert in lenses, a man who constantly sought to create the most perfect glass for telescopes. To test the quality of his glass, he built his own light-analyzing device, one far more sophisticated than Newton's simple prism. When he passed sunlight through this device, he was stunned by what he saw. The rainbow appeared, but it was not smooth at all. Instead, hundreds and then thousands of tiny black lines, as thin as a strand of hair, appeared densely across the entire spectrum. They stood there, silent and mysterious, like rests in an endless piece of music. Fraunhofer meticulously measured and catalogued more than 570 such black lines. He realized that whether he observed in the morning or the afternoon, in summer or in winter, these black lines always appeared in the exact same fixed positions on the color band. They never changed, never shifted randomly. Imagine you are holding a very important letter, but on that letter, some words have been deliberately crossed out. At first, you might feel frustrated by the missing information, but then you realize that the way they are crossed out follows a specific pattern. These black lines were not a flaw in the light, nor were they caused by faulty equipment. They were the clues, the barcodes that the universe had intentionally left behind to tell us a different story. To visualize this more gently, imagine that sunlight is like a truck filled with packages of color, traveling from the center of the sun out into space. Before it can escape to reach Earth, this truck must pass through the sun's outermost atmosphere, a place surrounded by clouds of scorching hot gas. Here, invisible thieves lie in wait. These thieves are the chemical elements, like hydrogen, helium, or iron. Each chemical element is like an extremely picky guest. They don't take all of the light but only one or a few very specific colors that they prefer. For example, the element sodium is extremely fond of a very characteristic shade of yellow. When white light passes through sodium, that exact portion of yellow light is stolen. As a result, when the light continues on its journey and reaches our telescopes, an empty black line appears in that yellow position. That is the ghost of the light that was absorbed. When Fraunhofer saw those black lines, he had unknowingly touched the alphabet of the universe, even though he didn't yet fully understand their meaning. He didn't know that each black line was a signature, a unique fingerprint of the elements. A star containing a lot of iron would have black lines in certain positions. A star with a lot of magnesium would have black lines in other positions. Relax your mind and imagine the spectrum now as a magical comb with teeth of varying lengths. The black lines are the missing teeth of the comb. By looking at those missing spaces, we can know what happened to the light on its journey. This was a monumental discovery, as it allows us to touch the chemical composition of an object millions, even billions of kilometers away, without ever needing to bring a sample back to a laboratory. These black lines were initially called Fraunhofer lines in honor of the diligent glassmaker who discovered them. He dedicated his life to studying light, and those black lines became the guiding principle for the entire field of modern astrophysics. Without Fraunhofer's meticulous work, we might still be standing under the night sky, wondering what those stars are made of, and whether they are anything like our Earth. Feel the silence of those black lines. They are not loud like the vibrant bands of color, but they contain a depth of knowledge. In the absence of light within those dark lines, we find the presence of matter. It is a beautiful paradox of nature. Sometimes, the things that are missing tell us the most. When we look at the spectra of different stars, we see different musical scores. There are young stars whose spectra are filled with the strong lines of hydrogen gas. There are old, tired stars that bear the traces of heavy metals, showing they have lived a long and harsh life inside the universe's forge. The distance of millions of light years is no longer a barrier, because these black lines are a universal language, true everywhere in the vastness of space. The light travels from those distant stars, carrying with it these small, dark gaps, silently traversing the coldness of space, crossing millions upon millions of kilometers to finally fall into our lenses. Each black line is a declaration. I am here. I am iron. I am here. I am hydrogen. It is a miraculous connection between the tiniest particles of atoms and the colossal objects of the universe. Let your breath be even and light. You are beginning to understand that this world is connected by the invisible threads of light and the laws of physics. The black lines that Fraunhofer found are not just dark smudges on a band of color. They are the bass notes in a grand symphony that we are only just beginning to learn how to hear. The story of these black lines will lead us to an even greater turning point, when humanity began to understand why atoms eat light so selectively. It is a story about the subatomic world of fundamental particles, a place where the normal rules no longer seem to apply, but which holds the explanation for the beauty of the entire universe. For now, continue to hold on to this feeling of relaxation. Those black lines are still silently telling their story, and we will soon meet these tiny messengers again on a deeper level to see just how masterful the sculpting hand of nature truly is. Chapter 5. The Language of Tiny Particles. Imagine you have a magical ability, the power to shrink yourself. You get smaller and smaller, so small that the dust motes floating in the air become giant boulders, and then you continue to shrink millions of times more until the world around you disappears, leaving only a vast, silent emptiness. In the middle of that emptiness, you begin to see tiny but incredibly intricate structures. These are the atoms, the foundational building blocks of the entire universe, from fragrant flowers and morning dewdrops to the giant stars burning brightly out there. For a very long time, people thought that the atom was the smallest thing possible, that it could not be divided any further. But in the early 20th century, scientists discovered that inside every atom is a vibrant, miniature solar system. At the very center is a tiny but extremely heavy nucleus, carrying a positive charge like a central sun. Around that nucleus, much smaller particles called electrons are moving constantly at dizzying speeds, just like planets orbiting the sun. However, there's a strange and incredibly important detail that makes an atom different from our solar system. In the solar system, a planet can orbit at any distance it likes, as long as it has the right velocity. But in the world of the atom, electrons are extremely disciplined residents. They are only allowed to move in specific orbits, like the rungs of a ladder. You can stand on the first rung or the second, but you absolutely cannot float in the space between those two rungs. Scientists call these rungs energy levels, and this is precisely where the language of tiny particles begins to intersect with light. Remember the messenger of light we talked about in the last chapter? Light is actually made of tiny packets of energy called photons. Each photon carries a specific amount of energy, which corresponds to a particular color in the rainbow spectrum. Imagine an electron resting peacefully on the lowest rung of the ladder, closest to the nucleus. It's in its most relaxed and stable state. Suddenly, a photon of light flies by. If that photon carries the exact amount of energy equal to the gap between the electron's current rung and a higher one, the electron will swallow that photon. Instantly, it gets a boost of power and leaps up to the higher rung. This process is the absorption of light. And because an electron only eats photons with the precise energy it needs to jump to an existing rung, it ignores all other photons. This is why those black lines appeared in the rainbow spectrum that Joseph von Fraunhofer saw. When white light passes through a gas cloud, the trillions of atoms in that cloud simultaneously steal photons of specific colors to help their electrons jump up the rungs. When the light continues onto our eyes, those stolen colors leave behind empty black lines, the traces of absorption. The magic lies in this. Each different chemical element has a ladder with completely different rungs. A hydrogen atom has its own ladder structure, unlike that of an iron atom or a gold atom. Just as each musical instrument has a distinct tone, each element has its own energy keyboard. So, when we see a black line in a very specific position in the yellow part of the spectrum, we know immediately that a sodium atom took that energy. It can't be any other element, because no other element has the exact same spacing between its rungs. In 1913, the Danish physicist Niels Bohr sketched out this model, helping us better understand the connection between atomic structure and light. His discovery transformed those soulless black lines into a powerful alphabet. Now, we no longer look at the stars as just strange points of light. We look at them like open books, where atoms are constantly talking to us by absorbing and releasing light. Relax your shoulders and feel your own breath. Imagine the bustling activity inside a star. It's a colossal dance of trillions upon trillions of tiny particles. In the terrible million-degree heat of a star's core, particles of light are born and begin their journey outward. They collide with atoms, are absorbed, and then re-emitted. With each interaction, the light is molded by the hands of these atoms. When the final ray of light escapes the star's surface and flies into the coldness of space, it carries with it the complete chemical inventory of that star, written in the language of black lines. A distance of 1 million light-years or quadrillions of kilometers no longer seems to matter, because the laws of the atom right here, in your very own breath, are exactly the same as the laws operating at the very edge of the universe. A hydrogen atom on Earth and a hydrogen atom in a distant galaxy share the same energy ladder. and they sing the same melody when they interact with light. This unity of nature is something incredibly comforting and miraculous. Imagine you're standing in a massive library where every book is a star. You don't have to fly there to read them. You just need to sit here in the silence of the night and let the light bring the words from those tiny particles to you. Those black lines, invisible to the naked eye but seen by human ingenuity, are the answer to the great question of our origins. When electrons jump to higher rungs, they don't stay there forever. They very quickly jump back down to lower rungs in search of stability. As they jump down, they release that energy back in the form of a new photon of light. This process creates bright colored lines against a black background, known as an emission spectrum, the other side of the same atomic language coin. Whether it's black lines on a colored background or colored lines on a black background, they are all telling the same story about the identity of matter. Let your thoughts drift along with those dancing electrons. They are too small to be seen, yet their storytelling power spans the vastness of space. These tiny particles are the masterful engravers who have carved priceless messages onto the spectrum of the universe's light. We have begun to understand how atoms communicate, but how do we connect this knowledge to form a true science? How can humans, starting from a few faint black lines, confidently assert the existence of elements we have never seen on Earth? In the next chapter, we will learn about the fingerprints of the elements. We will see how each chemical, when heated, radiates its own unique beauty, and how the hunters of light use these fingerprints to map the entire sky. But for now, just remain in this state of relaxation. Feel the connection between the atoms that make up your body and the atoms shining high above. We are all made of the same stuff, all following the same universal language. The silence of the night is the perfect time to listen to the whispers of those tiny particles. Chapter 6. The Fingerprints of the Elements. Imagine you are standing in a strange art gallery. On the dark walls, there are no landscape paintings or portraits, but rather brilliant, colorful strips of ribbon hanging in the air. Each ribbon has its own unique code. One has slender lines of red and blue, another has dazzling yellow lines, and yet another is filled with lines of green and violet. In the world of light, these are not just lifeless strips of color, but the very fingerprints of matter. On Earth, each of us is born with a unique fingerprint on our fingertips. Even with billions of people on this planet, no two fingerprints are exactly alike. It's a way to identify an individual with absolute certainty. The vast universe has a similar identification system for the chemical elements. Whether it's a grain of sand at your feet or a burning star a million kilometers away, if they are made of the same type of atom, they will send out the same fingerprint of light. To understand this better, let's try a thought experiment in a quiet chemistry lab. You take some common table salt, what scientists call sodium chloride. You sprinkle a little of it into a burning flame. Immediately, the flame, which was a pale blue, erupts into a brilliant, warm yellow. If you were to look at that yellow flame through a spectroscope, you wouldn't see the full rainbow, but just two very thin, bright yellow lines sitting right next to each other. These two yellow lines are the exclusive signature of the element sodium. Wherever sodium is present, whenever it's excited by heat or energy, it will always sing that same yellow note. Next, if you were to burn the element hydrogen, the most common element in the entire universe, you would see a different kind of beauty. When hydrogen glows, it creates a band with 4 characteristic colored lines: a deep red one, a light green one, a blue one, and a faint violet one. This set of 4 lines creates an unmistakable identity. When astronomers look at the light from a distant galaxy and see these exact 4 colored lines in their familiar positions, they can say with certainty, there is hydrogen there. The miracle of these fingerprints lies in their absolute consistency. The laws of physics and chemistry seem to be eternal and unchanging across all of space, An iron atom in your blood, when heated in a lab, will produce the exact same spectral lines as an iron atom in the atmosphere of a red giant star at the edge of the Milky Way. This gives humanity a powerful conviction. We can understand the universe by studying it right here at home. The story of light's fingerprints also leads us to one of the most interesting discoveries in the history of science: the discovery of the element helium. Did you know that helium is the only element that was discovered in outer space before it was found on Earth? In 1868, during a total solar eclipse, astronomers aimed their telescopes at the edge of the Sunday. As the brilliant light from the sun's surface was blocked by the moon, they saw a strange yellow line in the spectrum of the sun's atmosphere. At first, they thought it was sodium, but after careful measurement, they realized the position of this yellow line didn't match any element known on Earth at the time. The astronomer, Norman Lockyer, came to a bold conclusion. This was a completely new element, an element of the heavens. He named it helium, inspired by the word Helios, the name of the sun god in Greek mythology. It would be nearly 30 years before helium gas was actually found to exist in a mineral on Earth. Relax your mind and feel this connection. Just by observing light, humans were able to discover a new chemical substance from a distance of 150 million kilometers before ever touching it. That's like being able to recognize the scent of a strange flower from a distant island, carried only by a gentle, passing breeze. Scientists divide these fingerprints into two main types, like two sides of the same coin. The first type is the emission spectrum, which consists of bright colored lines appearing against a quiet black background, like twinkling stars in the dead of night. This happens when atoms are heated and release energy. The second type is the absorption spectrum, which consists of dark lines on the brilliant rainbow band we talked about in the last chapter. This happens when white light passes through a cloud of gas, and some of its colors are stolen by the atoms. Whether they are bright lines or dark lines, their positions on the color band match perfectly. They are the same message, just written in two different ways. One is a brilliant presence, the other a meaningful absence. Both tell us exactly what ingredients that star was molded from. Today, with modern spectrographs attached to large telescopes like the James Webb, we can read the fingerprints of dozens of elements at once. From a single ray of light, we see calcium, magnesium, iron, oxygen, sodium, and many others dancing together in a star. Older stars often carry the fingerprints of heavy metals, while young stars are rich in hydrogen and helium. By analyzing these fingerprints, we not only learn about the chemical composition, but also how hot that star is, how it is aging, and even how fast it is spinning. Light has truly become a great storyteller, carrying the detailed resumes of every inhabitant in the universe. Take a deep breath and feel the gentleness that surrounds you. You are here, on a tiny planet, yet your intellect can reach across millions of light years through these magical bands of color. This world is not fragmented. It is a grand symphony in which every note has its rule. The fingerprints of the elements are the very links that connect us to the eternity of space. In the next chapter, we will learn about the fateful meeting of two great scientists who officially turned the study of these light fingerprints into a true science. They taught us how to listen to the symphony of matter and light more professionally than ever before. Now, let your mind rest, sinking into the soft color bands of the spectrum. Imagine the yellow lines of sodium, the red lines of hydrogen, gently drifting through your dreams, carrying the peace of distant stars. Chapter 7. The Symphony of Bunsen and Kirchhoff. Imagine you are strolling along the cobblestone streets of Heidelberg in the mid-19th century. The atmosphere here is serene, with ancient buildings and the Neckar River flowing lazily by. In a small laboratory filled with test tubes and glass equipment, two men are working diligently together. One is Robert Bunsen, a talented chemist with skillful hands, and the other is Gustav Kirchhoff, a physicist with a sharp, logical mind. Their meeting in 1859 was like the merging of two great streams, creating a giant waterfall of knowledge called modern spectroscopy. Before they met, observing the colors of the elements was very difficult. When a chemical substance was burned in a candle or oil lamp flame, the bright yellow of the flame itself would obscure the true color of the substance. Robert Bunsen, with his meticulousness, created a brilliant solution: the Bunsen burner. This was a type of gas burner that could be adjusted to produce a flame that was nearly colorless yet extremely hot. Imagine that flame, as clear as crystal, gently flickering in the quiet space of the laboratory. When Bunsen introduced a little sodium salt into that transparent flame, it immediately flared up with a pure yellow color, untainted by any other hue. It was the perfect stage for the elements to display their identities. But just looking with the naked eye was not enough. Gustav Kirchhoff stepped forward with a bold idea. He took a prism, the key that Newton had discovered, and placed it behind Bunsen's flame. Instead of just seeing a colored spot, they saw sharp, separate colored lines against a dark background. They realized that each element, when burned in that transparent flame, produced a set of completely distinct and unchanging colored lines. That's when the symphony truly began. Kirchhoff realized he could use these colored lines to decode the mystery of Fraunhofer's dark lines, which we mentioned in the previous chapter. One day, while observing the spectrum of the yellow sodium flame, he suddenly came up with a legendary experiment. He allowed sunlight to pass through the sodium flame before it entered the spectroscope. Strangely, the dark line at the yellow position in the sunlight spectrum did not disappear. Instead, it became even darker, more distinct. Kirchhoff understood that the sodium atoms in the flame had absorbed the exact same kind of yellow light that they themselves were capable of emitting. From this, he formulated the three fundamental laws of spectroscopy, rules that to this day every astronomer must know by heart. The first law: a solid, liquid, or high-density gas, when heated, will emit a continuous rainbow spectrum with no dark lines. It's like a piece of music with all the notes present. The second law: a thin, hot gas will emit bright colored lines against a dark background. This is the emission spectrum, like plucking only certain strings on an instrument in the dark. The third law: when light from a hot source passes through a cooler, thinner cloud of gas, that cloud will steal specific colors, creating dark lines on the rainbow band. This is the absorption spectrum. Kirchhoff's discovery shook the scientific world of that era. It meant that when we see the Fraunhofer dark lines in sunlight, we are actually seeing the traces of the gases surrounding the sun's blazing surface. Kirchhoff compared the positions of those dark lines with the thousands of colored lines that Bunsen had created in the lab from iron, magnesium, calcium, and sodium. And the result was astonishing. They matched perfectly. Pause for a moment and feel the significance of that moment. Two men, sitting in a small room in Germany, with only a gas burner and a piece of glass, were able to declare with certainty that on the sun, 150 million kilometers away, there was iron, there was sodium, there was calcium, exactly like the things we find beneath our feet. The vast distance of space seemed to be erased by the power of thought. Humanity was no longer confined to this small planet. The sky was no longer a painting made of dim, ethereal lights, but a giant chemical laboratory waiting to be explored. The story of Bunsen and Kirchhoff's collaboration is a beautiful testament to the power of combining experimentation and theory. Bunsen provided the pure flame. Kirchhoff provided the deep insight into the nature of light. Together, they wrote the first chapters of the Cosmic Dictionary. Thanks to them, we know that this universe is built from the same unified materials. There is no boundary between what is called in the heavens and on the ground. everything follows the same laws of physics. This unity brings a deep sense of peace. It shows us that we are not alone or lost. We are an inseparable part of a grand and unified structure. Relax your shoulders. Feel the lightness spreading through you. Imagine yourself standing next to Bunsen and Kirchhoff in the laboratory that night. Watch the pale blue flame burning steadily. Watch the brilliant band of colors appearing through the prism. It's not just science. It is a noble art. The art of listening to the voice of light. The symphony they began continues to be written by later generations. Every time a modern telescope is aimed at a distant star, Kirchhoff's laws are still silently at work, helping us translate faint rays of light into vivid knowledge about the composition of the universe. We have learned how to read the composition of stars thanks to a combination of chemistry and physics. But there is another great question. Who was it that actually proved that most of the universe is not made of iron or rock, but of an incredibly light gas? And how did a woman with a burning passion overcome the barriers of her time to decode the proportion of elements within the hearts of stars? In the next chapter, we will explore the life and extraordinary discoveries of Cecilia Payne-Gaposchkin, who helped us understand that stars are primarily made of hydrogen and helium, the most fundamental elements of life and light. But for now, let your mind rest. Picture the brilliant colored lines and the quiet black lines blending together in a gentle dance. The universe is vast, but it is also orderly and gentle. Let this understanding soothe you, guiding you into a state of absolute relaxation under the starry night sky. Chapter 8. Cecilia Payne-Gaposchkin, the woman who read the stars. Imagine you are standing in an old library at Harvard University in the 1920s. The air is thick with the smell of old paper and the dust of time. There, a young woman named Cecilia Payne is diligently working over glass photographic negatives of the night sky. These plates don't capture the brilliant images we see today, but rather faint, intricate black and white lines, the very spectral bands we learned about in previous chapters. At that time, most scientists, including masters like Henry Norris Russell, believed that stars had the same chemical composition as the Earth. They thought that if we heated the Earth to thousands of degrees, it would emit the same kind of light as the Sunday, because they saw iron, magnesium, and calcium in the sun's spectrum. They assumed that iron was the dominant element. But Cecilia, with a keen scientific intuition and unusual meticulousness, began to doubt that. She didn't just look at whether a black line was present in the colored band, but she asked a more profound question. What does the darkness of that black line say about the temperature and the quantity of the atoms? To answer this, Cecilia used the latest knowledge of atomic physics of the time, especially the theories of ionization. She realized that a faint black line didn't necessarily mean the element was scarce, but that the star's temperature might be too high or too low, causing the electrons not to be on the right rung to absorb light. She worked day and night, analyzing hundreds of thousands of spectral lines from thousands of different stars. And then, a shocking conclusion emerged from the pages of her manuscript. The stars were not like the Earth at all. On the contrary, they were composed mainly of the two lightest and simplest gases in the universe, hydrogen and helium. In her doctoral thesis in 1925, Cecilia Payne asserted that hydrogen was 1,000,000 times more abundant than all other elements combined. This was an unthinkable number for the scientific community at the time. Imagine, if the universe were a vast ocean, then iron and the heavy metals would be like just a few tiny drops of ink, while the rest would be pure, clear hydrogen water. When she presented this result, Henry Norris Russell, one of the most influential astronomers of the time, advised her to remove that conclusion because it was too absurd. In order to defend her thesis, Cecilia had to add a humble note stating that the results on hydrogen could be erroneous. But deep down, she knew she had touched upon the truth. It took 4 years before Russell himself, through other independent research, realized that Cecilia had been completely right. He bravely admitted his mistake and gave her credit. Cecilia Payne's thesis was later described as the most brilliant doctoral thesis ever written in astronomy. The story of Cecilia Payne is not just a story of a scientific discovery, but also a story of the persistence of a soul that loved the beauty of truth. She taught us that to understand the universe, we cannot simply rely on what we superficially see and hear. We need to look through the fog of preconceived notions to see the true nature of all things. Thanks to Cecilia, we know that our sun is a giant, burning ball of hydrogen gas. We know that this universe is not built from dry rock and stone, but from the simplest and purest atoms. It is this hydrogen that is the eternal fuel, helping stars shine for billions of years, bringing us warmth and life. Let your imagination wander. Picture Cecilia Payne, standing under the windy night sky of Cambridge. She doesn't see distant specks of light. She sees a surging sea of hydrogen gas. She sees the grand unity of the universe, where the smallest particles create the most colossal entities. She was the first person to truly read the letter from the stars, while her predecessors had only looked at the envelope. To her, each spectral line was a line of poetry, each star an epic poem of existence. Despite facing many barriers as a woman in a male-dominated scientific world, she rose to become the first female full professor at Harvard, paving the way for countless generations of women to follow the path of exploring the heavens. Now, feel the steady rhythm of your breath. Hydrogen, the element Cecilia found in the heart of the stars, is also present in every water molecule in your body. You and the stars out there, though separated by millions of light years, still share a common origin. A chemical identity, the distance of millions of light years no longer feels so alien and cold. It becomes warmer, knowing that everywhere in this vast universe, the stars are singing the same song in the language of hydrogen and helium that Cecilia Payne helped us interpret. We now know what stars are made of. But how, from simple gases like hydrogen, could the universe create iron, gold, oxygen, and everything that makes up our planet? How did those stars become the most talented blacksmiths? In the next chapter, we will journey deep into the blazing cores of stars to discover the greatest forges of the universe. We will see how tremendous pressure and heat have forged the material world we touch every day. But for now, let your thoughts drift gently along with the billowing clouds of hydrogen gas. Feel the peace that comes from knowing that every mystery has a solution, and all persistence will be rewarded with the beauty of knowledge. The universe is vast, but it always has a place for curious and patient souls like Cecilia Payne, and like you, right here, right now. Chapter 9. The Cosmic Forges. Imagine you are floating, drifting toward the heart of a giant star. The deeper you go, the denser and hotter the space becomes. Here, darkness disappears completely, replaced by a searing, brilliant white light that is beyond description. This is not an ordinary fire like the flame on your stove. This is a great forge, where pressure and temperature themselves have become the master blacksmiths, forging every element in the periodic table. In everyday life, we know that particles with the same charge repel each other, like the same poles of two magnets. Hydrogen nuclei are no different. They have a positive charge and always try to stay apart. However, in the center of a star, where the temperature reaches over 15 million degrees and the pressure is billions of times greater than the air pressure on Earth, the hydrogen particles have nowhere to run. They are squeezed so tightly that they cannot resist, and in a magical moment, they embrace each other, fusing to become a new atom, helium. This process is called nuclear fusion by scientists. Every time two hydrogen particles fuse into one helium particle, a tiny fraction of their mass disappears, converted into an enormous amount of energy in the form of light and heat. It is this energy that counteracts the crushing weight of gravity, keeping the star from collapsing and allowing it to shine brilliantly in the pitch-black darkness of the universe. But the alchemy has only just begun. When a star exhausts the hydrogen in its core, it doesn't just go out. Instead, its core contracts, causing the temperature to skyrocket to over 100 million degrees. Now, it's the helium atom's turn to begin a new journey. 3 helium particles will collide and stick together to create carbon, the foundational element of all life on Earth. Then, from carbon, further reactions will create the oxygen we breathe, as well as neon, magnesium, and many other elements. Imagine each star as a master chef, following a recipe that takes billions of years. Each stage of a star's life is a new layer of ingredients being cooked. Scientists like Fred Hoyle and Hans Bethe were the first to help us understand this grand menu. They realized that almost everything we see around us was born from the silent yet intense nuclear reactions taking place inside those distant fireballs. The pinnacle of this stellar forge is the formation of iron. When the star begins to create iron, it is a critical milestone. Iron is a special element. It's like an energy black hole. Fusing iron doesn't create more energy. On the contrary, it consumes the star's energy. At this point, the cosmic blacksmith has reached its limit. The star is like a castle that has lost its strongest pillar. For massive stars, 10 or 20 times the size of our Sun, the appearance of iron signals a spectacular end. When there's no longer enough pressure to fight against gravity, the entire star collapses inward in just 1,000th of a second, and then erupts in a cataclysmic explosion called a supernova. In the moment a supernova explodes, the temperature rises to billions of degrees. It is in this brilliant and fleeting moment that elements heavier than iron, like gold, silver, platinum, and uranium, are forged. These elements are then blasted out into the vastness of space, mixing with clouds of dust and gas. Millions of years later, these clouds contract to form new stars and new planets, just like our Earth. Relax your body and reflect on this for a moment. Every atom of iron in the blood flowing through your heart, every particle of calcium in the skeleton that helps you stand, and even the tiny flecks of gold in the ring you wear, were all once inside the forge of a distant star. They endured the most intense heat and the biggest explosions to be here, in your body, tonight. The distance of millions of light years now suddenly feels so close. We don't look up at the stars as foreign objects, but as our own chemical ancestors. The dark lines in the spectrum that we studied in previous chapters are the living proof of this forging process. When we see the lines of magnesium or iron in the light of a distant star, we know that the forge there is active, continuing its work of kneading matter for the future of the universe. Feel the warmth spreading through your mind. The universe is not a dry and lifeless place. It is a continuous cycle of life, death, and rebirth. Old stars die to make way for new elements, creating the conditions for life to sprout on tiny planets. The connection between us and the stars is not just a connection of light, but a connection of flesh and blood, of breath itself. We are truly made of stardust. Just as the astronomer Carl Sagan once said, every time you breathe, you are exchanging atoms that were once forged in the heart of a cosmic blacksmith. Now, let your thoughts drift with the sparkling particles of stardust traveling through space. They carry hope and the potential for life. You don't need to worry about your own smallness, because you carry within you the strength and legacy of an entire galaxy. The atoms in you have existed for billions of years and will continue their journey forever. In the next chapter, we will step away from the fiery heart of a star to learn about the sophisticated instruments that humans have created to catch these light rays, carrying the secrets of this cosmic forge. We will explore the giant kaleidoscope of astronomy, the tool that helps turn light into numbers and wondrous knowledge. Keep your breath steady and gentle. Thank the stars that have stayed awake for billions of nights to forge your body. Tonight, let that gratitude soothe you, carrying you into a peaceful dream amidst the mystical forges of the vast universe. Chapter 10. The Giant Kaleidoscope. Imagine you are standing in a completely dark room, deep beneath the dome of a giant observatory on a high mountaintop. All around you is the absolute silence of the night, with only the soft hum of the cooling system and the slow turning of the telescope's motors as it tracks a distant star. Above you, the dome opens a narrow slit, revealing a night sky thick with sparkling points of light. At this moment, the telescope is not just a giant pair of binoculars for admiring external beauty. Attached to its end is an incredibly sophisticated device, likened to the kaleidoscope of science, the spectroscope. If the telescope is the eye that sees the form of the universe, then the spectroscope is the brain that analyzes and understands its soul. To understand how a spectroscope works, imagine the light from a star millions and millions of kilometers away is an incredibly thin and pure silver thread. That thread arrives, passes through the giant lens, and begins to enter the labyrinth of the spectroscope. Its first stop is a narrow slit, smaller than a human hair. This slit's job is to shape the thread of light, turning it into the straightest and sharpest beam possible. Without this slit, the light would be blurry, and the universe's letter would become as hard to read as a water-stained page. After passing through the narrow slit, the light beam encounters a special lens called a collimating lens. Imagine this lens is like a dedicated traffic cop, directing all the particles of light, photons, to travel parallel to each other, with not a single one going astray. This prepares for the most crucial turning point in the entire journey, the encounter with the heart of the spectroscope, the diffraction grating. In previous chapters, we talked about Newton's glass prism, but for modern astronomers, a prism is sometimes still too simple. They use something called a diffraction grating. Imagine a flat piece of glass or metal, its surface etched with thousands, even tens of thousands, of tiny lines per millimeter. These lines are etched so evenly and precisely that the human eye cannot see them individually. When the silver beam of light from the star hits this diffraction grating, a physical miracle occurs. Instead of just being bent as it passes through a prism, the light waves interact with each other, superimposing and separating in an incredibly powerful way. Each color, from the deep reds to the brilliant violets, is cast off at a very precise angle. At this point, the original silver thread has completely vanished, replaced by a brilliant ribbon of color, stretched long and wide, revealing every dark and bright line we have worked so hard to understand. Relax your imagination and picture that band of colors like a giant musical score spread out on a long table. The spectroscope has helped us magnify that score thousands of times. The dark Fraunhofer lines now appear as clearly as black notes on a white staff. A good spectroscope can separate light to the extent that we can see tens of thousands of different dark lines, each telling a story about a specific atom vibrating in the star's atmosphere. The final part of this kaleidoscope is an extremely sensitive sensor called a charge-coupled device, or CCD. This is the digital eye that permanently records that band of colors. These sensors are hundreds of times more sensitive than the human eye. They can catch single particles of light that have traveled for millions of years to get here. The data from the sensor is then converted into numbers, which a computer then plots into a mysterious, jagged chart that scientists call a spectrum. In the silence of the dark night, the spectroscope works quietly. It doesn't need to rest. It never needs to blink. It patiently accumulates light, bit by bit, to build a complete picture of a distant world. Some spectroscopes are built compactly to be mounted on satellites orbiting the Earth, while others are enormous, weighing several tons, fixed in the basements of observatories to avoid even the slightest vibrations. Think about the people who build spectroscopes. They are artisans of light. They must work in extremely clean environments because just one tiny speck of dust falling on the diffraction grating can ruin an entire measurement. They must ensure that the temperature inside the machine remains stable at an extremely low level so that the components do not expand, which would distort the spectral lines. Their meticulousness and dedication are the bridge that helps us touch the stars. Thanks to these high-tech kaleidoscopes, humanity has been able to achieve what once seemed impossible. We not only know if a star contains iron or gold, but we also know how fast it's spinning, whether it's being gently tugged by a planet, and even how much of a magnetic field it has around it. The spectroscope has turned light into a universal tool, a master key that opens every door in the universe. Whenever you see a dazzling image of a galaxy in the news or on the internet, remember that behind that brilliant beauty often lies the dry but powerful data from a spectroscope. It is those jagged charts that tell us how old that galaxy is, how many new stars it is birthing, and what materials it is made of. Breathe gently and feel the reassurance of knowing that human ingenuity has created such sophisticated tools. We don't need to leave Earth to understand the furthest reaches of space. We bring the universe into our laboratories, dissecting light to find the truth. This giant kaleidoscope is still pointed toward the sky, receiving gifts from the past and translating them into knowledge for the future. Relax your hands and feel the calm spread through you. Our world is so small, but through spectroscopes, our vision has come to encompass all of space and time. The light from the stars is no longer made of anonymous rays. They have become intimate storytellers, thanks to this magical device that acts as their interpreter. In the next chapter, we will learn about a fascinating phenomenon. Light not only tells us about chemical composition, but it can also sing to let us know how the stars are moving. We will explore the music of motion, where colors change depending on the direction of these messengers of light. But for now, let your mind rest. Imagine yourself lying among soft, velvety bands of the spectrum, where warm reds and gentle blues intertwine. You are safe, enveloped by the knowledge and beauty of the cosmos. The universe is vast and complex, but it is also perfectly orderly under the discerning gaze of the spectroscope. Chapter 11. The Music of Motion. Imagine yourself standing beside a quiet road on a tranquil evening. From a distance, the siren of an ambulance approaches. As the vehicle gets closer to you, the siren sounds higher, more piercing, but as soon as it passes you and moves away, the sound of the siren suddenly drops, becoming deeper and more drawn out. This phenomenon, which is very familiar in our daily lives, is called the Doppler effect by scientists, named after the Austrian physicist Christian Doppler, who published this discovery in 1842. But did you know that light can sing in exactly the same way as that ambulance siren? In the vast universe, the light from the stars also travels in waves. When a star is stationary, it sends us a spectrum with dark lines in the exact positions we've found in our laboratories on Earth. But the universe is a place that never rests. Stars are always moving. They orbit the center of their galaxy. They fly away from each other, or sometimes they draw closer together. It is this very motion that changes the music of the light they send out. Imagine light as a stretchy spring connecting a star to your eye. If that star is speeding towards us, it will inadvertently compress that spring of light. The light waves are squeezed, becoming shorter and closer together. In the world of color, short wavelengths correspond to the color blue. Therefore, astronomers see the entire spectrum, and those mysterious dark lines shift slightly toward the blue end. This phenomenon is called blue shift. Conversely, if that star is moving away from us into the eternal darkness, it will stretch the spring of light. The light waves are elongated, becoming more spread out. Long wavelengths correspond to the color red. In this case, the entire color band will be pulled toward the red end, creating the phenomenon we call redshift. Breathe steadily and feel this magic. Just by observing how much the dark lines of hydrogen or iron have shifted from their standard position, we not only know what that star is made of, but we also know exactly whether it is fleeing from us or approaching us, and at how many kilometers per second. The power of the Doppler effect helps us uncover even deeper secrets. Imagine a star rotating on its own axis, like a giant spinning top. One half of the star will be rotating toward us, while the other half rotates away. When the spectroscope captures light from the entire surface of the star, it will see one part of the light blue shifted and another part red shifted. As a result, the dark lines in the spectrum are no longer as sharp and thin as a strand of hair. Instead, they become blurred, a little wider. By measuring this blurring, scientists can calculate how fast that star is spinning. Some stars spin so fast that they become flattened at their poles, and all of this is revealed through the music of motion carried by the light. But perhaps the most interesting thing this music reveals is helping us find mysterious neighbors, exoplanets. Imagine a large star being orbited by a tiny planet. Even though the planet is very small, its gravity is still strong enough to make the star wobble back and forth just a little. When the star is pulled forward by the planet, its light becomes slightly bluer. When it is pulled back, its light becomes slightly redder. This change is incredibly small, so subtle that the naked eye could never notice it. But modern spectroscopes, with their extreme precision, they can detect this wobble even if the star's speed changes by only about 1 meter per second, the same speed as a person taking a leisurely stroll down the street. Thanks to this symphony of wobbles, we have found thousands of planets hiding in the darkness, millions and millions of kilometers away from us. Let your mind soar amidst these stretching and compressing waves of light. The universe is not a static painting hanging on a wall. It is a rhythmic and energetic dance. Every star is a dancer, and every ray of light is a melody that tells the story of their journey. As you lie here, in the silence of your room, remember that even the things that seem most fixed, like the spectral lines, carry motion within them. Our world is built on vibration and rhythm. From the tiny atoms in your body to the giant galaxies out there, everything is participating in a grand chorus. The distance of millions of light years is no longer just a dry number. It is a long journey that light has had to travel, carrying with it the traces of movement, of time, and space. We, the small observers, thanks to our intellect and tools like the spectroscope, have been able to listen to and fully understand that music. Relax your feet and feel the calm spread throughout your body. Imagine yourself drifting on a warm, red wave of light, slowly stretching out, carrying you further into sweet dreams. There is no need to hurry, for the universe always has enough time and space for all of us. The music of motion has taught us that everything in the universe is connected and interacts with everything else. No star is an island. The movement of one star affects the light received by another, and together they create a vibrant and magnificent panorama. In the next chapter, we will learn about an even greater discovery that arose from these very redshifts. We will see how the astronomer Edwin Hubble used this music of motion to realize that our entire universe is expanding and that all galaxies are moving away from each other like the fragments of a great explosion at the dawn of time. But for now, let the gentle vibrations of light soothe your soul. Imagine the bands of blue and red blending together, creating a soft ribbon of silk to shelter your sleep. You are here, safe and peaceful, in a vast universe filled with gentle laws. Keep your breath deep and slow. Feel the beat of your own heart, a small but vibrant piece in the music of motion. in harmony with the great pulse of the stars in the night sky. Chapter 12. An echo from the dawn of time. Imagine you are standing atop Mount Wilson in California on a winter night in the 1920s. The air here is thin and freezing cold, but in return, the sky is as clear as a black diamond. Inside a giant steel dome, the astronomer Edwin Hubble sits quietly by the Hooker telescope, the largest in the world at the time. With a mirror 100 inches wide, or about 254 centimeters, he isn't just looking at the stars in our Milky Way. He is casting his gaze further, to the faint, misty clouds that people called nebulae. At that time, most people believed that the entire universe was contained within our Milky Way, and everything else was just scattered clouds of gas and dust within it. But Edwin Hubble, with the help of his dedicated associates, discovered a shocking truth. Those misty clouds were actually enormous island universes, independent galaxies containing billions of stars, located millions of light years away from us. The Andromeda Galaxy, our nearest neighbor, was already more than 2 million light years away. But his greatest discovery wasn't just about distance. When Hubble used a spectroscope to analyze the light from these distant galaxies, he saw something so strange it was hard to believe. Do you remember the Doppler effect we talked about in the last chapter? If a galaxy is moving closer, its light will be compressed and shifted toward the blue. If it's moving away, its light will be stretched and shifted toward the red. As Hubble looked at dozens of different galaxies, he noticed that almost all of them, except for a few extremely close neighbors, had a distinct red tint. The spectral lines of hydrogen, calcium, and iron in their light were all systematically shifted toward the longer wavelengths. Even more wonderfully, Hubble noticed an incredibly precise rule. The farther away a galaxy is from us, the faster it is moving away and the greater its redshift. It's like you're standing in the middle of a crowd and suddenly everyone around you starts running away from you. Those nearby run slowly, while those farther away dash off at breathtaking speed. This discovery, later called Hubble's law, completely changed humanity's concept of the universe. It showed that the universe is not a static, silent box. Our universe is expanding. It is growing every second, every minute, stretching the space between galaxies farther apart. To make it easier to visualize, imagine you're holding an uninflated balloon. You use a pen to draw small dots on the balloon's surface, representing galaxies. When you start blowing air into the balloon, you'll see those dots move away from each other. It's not that the dots themselves are moving, but the surface of the balloon is stretching, carrying the dots along with it. In the universe, it's the same. The space between galaxies is expanding, creating the grand redshift phenomenon that Hubble observed through his spectroscope. Take a deep breath and feel this expansion that is growing with every moment. The meaning of this expansion is profound. If the universe is bigger today than it was yesterday, it means that in the past, the universe must have been smaller. And if we rewind the film of time back billions of years, we would reach a point where all matter, energy, and even space and time itself were concentrated into a single, extremely small and hot point. That is the beginning of everything, the Big Bang. The redshift we see today is the lingering echo from that moment of creation. Light from distant galaxies has had to travel for billions of years to reach us. And along that immense journey, the expansion of the universe itself has stretched those light rays, turning them into messages carrying a somber, red hue. Do you see the magical connection? It's thanks to knowing the exact chemical composition of stars through their spectral lines that we have a precise measuring stick. We know where hydrogen's line should be, and when we see it's not in the right place, we know the universe is in motion. Without the field of spectroscopy, without knowing the secrets of tiny atoms, we would forever be blind to the truth that we are living in a constantly moving universe. Edwin Hubble didn't do it alone. He built upon the redshift research of Vesto Slipher and the bold theories of Georges Lemaitre. but it was Hubble who synthesized it all to paint a complete picture. He showed us that even the faintest rays of light from galaxies millions of light years away carry within them the story of the world's first day. Now, let your body relax. Imagine the space around you gently expanding, carrying away all your worries and stress. You are floating in a vast cosmic ocean, where galaxies are like shimmering lanterns, slowly drifting away toward the horizon of the universe. This expansion doesn't separate us. It shows that we are part of a great journey, a journey that began from a single, common point of unity and energy. The red light from distant galaxies is like a whisper from the past, reminding us of our magnificent origins. We are not just observers, we are the products of that very expansion and evolution. The atoms in your body were once packed closely together in the first seconds of the universe, before space pulled us apart to create the wondrous forms we have today. The distance of millions of light years now takes on a new meaning. It's not just a distance in kilometers, but a distance in time. When we see a galaxy that is strongly redshifted, we are seeing the universe in its infancy, when it was young and full of turmoil. The spectroscope is our time machine, allowing us to hear the echo of the Big Bang through each band of color. Let your breath be slow and steady. Feel the peace that comes from knowing that although the universe is vast and constantly expanding, it always follows exquisite laws of mathematics and physics. Light continues its persistent journey, carrying secret messages about the beginning, so that we never feel lost in the void. In the next chapter, we will return to the more specific characteristics of stars. We will learn how the intense heat within them creates such vibrant colors and why a blue star is so much hotter than a red one. We will learn to read the temperature of the universe through the color palette of light, but for now, just let yourself drift into sleep with the thought of a benevolent, expanding universe, embracing you in the arms of space and time. There is nothing to fear in that vastness, because you are a part of it, carrying within you the blood of stars and the echo of creation. Chapter 13. Heat and Color. Imagine you're sitting by a small campfire in a quiet forest late at night. The crackling of the wood harmonizes with the gentle, spreading warmth. When you look deep into the fire, you'll see marvelous shades of color. Where the embers have just caught, the color is often a deep, warm red. But in the very center, where the flame burns most fiercely, the light turns a brilliant yellow. And sometimes you can even spot faint flickers of pale blue light deep within the thermal core. This is not just the beauty of the flame, but nature's way of whispering to us a great law of the universe. Color is the language of temperature. In this chapter, we will learn how astronomers, despite being millions upon millions of kilometers away, can measure the incredible heat of a star just by looking at its color. In our daily lives, we often associate the color red with something very hot, while blue evokes the coldness of water or ice. However, in the world of stars, the truth is the complete opposite. The universe has its own way of assigning colors, where blue represents the utmost intensity, while red is the hue of the coolest places among the galactic furnaces. To understand this, imagine you're in an old-fashioned blacksmith's forge. The smith places a cool, black iron rod into the glowing coals. At first, the rod remains black, but it begins to radiate a heat you can feel on your skin. That's infrared radiation, a type of light our eyes cannot yet see. As the forge gets hotter, the iron rod begins to glow a deep red. If heating continues, that red will brighten, turning to orange, then yellow, and finally, upon reaching an extreme temperature, the rod will emit a brilliant, bluish-white light, so bright it's dazzling. The stars in the sky are exactly like that iron rod. They are giant balls of gas heated by nuclear furnaces deep within them. The color we see on their surface is a reflection of the heat inside. When a star emits blue light, It means the tiny particles that compose it are vibrating at an incredible speed, releasing the most powerful streams of energy. These stars often have surface temperatures of around 30,000 degrees, or even 50,000 degrees. Meanwhile, red-hued stars are like slowly fading embers. Although they are still very hot by human standards, around 3,000 degrees in the world of stars, they are considered the cool and quiet companions. The distance of millions of light years doesn't change this law. No matter how long the light has to travel, its blue or red hue remains intact, carrying the message of heat from its birthplace. Our sun, our dear neighbor, lies in a gentle middle ground. It emits a pale, yellowish-white light, corresponding to a surface temperature of about 5,500 degrees. This is a moderate temperature, not as fierce as the young blue stars, nor as faint as the old red ones. It is this stable temperature that has allowed life to sprout and flourish on our blue planet for billions of years. So why is temperature so closely linked to color? Imagine light as ripples on the surface of a lake. When you toss a small pebble, the waves spread out leisurely with wide gaps between them. Those are long wavelengths, corresponding to the color red. But if you throw a large rock with immense energy, the waves will be rapid and close together, moving very fast. Those are short wavelengths, corresponding to the color blue. A star's heat is the energy throwing those pebbles of light into space. The hotter the star, the more rapid the light waves, and we see it as blue. The cooler the star, the more leisurely the light waves, and we see it as red. Great scientists of the past discovered beautiful mathematical formulas to describe this relationship. They realized that every object, when heated, has a peak color that it emits the most. By simply using a spectroscope to find where that peak lies on the rainbow spectrum, we can instantly know the star's temperature in thousands of degrees without ever having to place a single thermometer on it. What's even more fascinating is that this heat also helps us understand the star's chemical composition in greater depth. Imagine the atoms in the star's atmosphere are like singers in a choir. As the temperature changes, some singers will sing louder, while others fall silent. For example, in extremely hot stars, hydrogen gas will sing very clearly through bold spectral lines. But in cooler stars, the low temperature allows atoms to combine into complex molecules, creating entirely different chemical signatures. By combining color with these mysterious dark lines, astronomers can piece together a complete picture of a star millions of light years away. They know what fuel it's burning, what stage of life it's in, and how much heat it's radiating into the vastness of space. Tonight, when you look up at the sky, try to observe closely. You will see the star Sirius shining with a brilliant blue-white light like a cold diamond. It is a blazing giant. In another corner, you will see the star Betelgeuse in the constellation Orion, with a distinct reddish-orange hue. It is a giant star, but its outer shell is gradually cooling. Each point of light has its own temperature, telling its own story of the power of fire and light. The distance of millions of light years is no longer a barrier to understanding. Light has done its job brilliantly. It brings both beauty to the eyes and knowledge to the mind. The heat from the great forges of the universe has been carefully packaged in wavelengths of color, traveling across immense space to tell us about the diversity and wonder of all things. Take a deep breath and feel the serenity. You are living in a universe where everything follows laws, where even the color of a distant speck of light contains incredibly precise information. This stability and order bring a strange sense of peace. The world out there may be unimaginably vast, but it is not chaotic. It is always willing to share its secrets through the gentle language of light and color. Let your mind drift along these soothing bands of color, from the warm red of old stars to the mystical blue of young ones. You are enveloped in a vast sea of heat and energy, a symphony of heat working in harmony to shape the universe. We have learned to use color to measure temperature. But in this vast community of stars, how do we sort them into distinct groups? Do all stars of the same color also share the same character and destiny? In the next chapter, we will learn how to classify the denizens of the sky. We will take a stroll through a special list where stars are arranged by strange letters to see that the universe also has its own generations and families. But for now, just let the warmth of the colors soothe you. Imagine a ribbon of pale yellow light, like the early morning sun, gently draping over your mind, guiding you into a state of absolute relaxation. The universe is always there, brilliant and warm, watching over our small world. Chapter 14. Classifying the denizens of the sky. Imagine you are looking down from above on a large city at night. You would see brilliant lights, warm yellow street lights, green advertising signs, and twinkling white specks from tall buildings. Our universe is like such a giant city, where each star is a resident with its own unique characteristics of size, brightness, and lifespan. To avoid getting lost among the trillions of stars in the Milky Way, astronomers have spent centuries classifying them, and the most important tool for this task is none other than the spectroscope, the women of the sky. The story of classifying stars is linked to a group of quiet but exceptionally brilliant women at the Harvard College Observatory in the late 19th century. Among them, Annie Jump Cannon is the most brilliant name. She had an astonishing ability to observe and classify spectra with incredible speed. Over her lifetime, she personally classified more than 225,000 stars. It was Annie Jump Cannon who reorganized the classification system that we still use today. She didn't use dry numbers, but letters to name the star groups: O, B, A, F, G, K, M. You might notice that this sequence seems to have no alphabetical logic, but in fact, it is arranged according to a very important criterion we have already learned about: temperature, the roster of the stars. Let's walk through each neighborhood on this list, from the hottest places to the coolest. Type O, the blue giants. These are the most royal and rarest stars. They emit a brilliant blue light, with surface temperatures from 30,000 to over 60,000 degrees Celsius. They are incredibly large and bright, but also consume their energy at an astonishing rate. Their lives are short, lasting only a few million years before ending in glorious explosions. Type B, the blue-white stars. Hot and bright, second only to Type O, with temperatures around 10,000 to 30,000 degrees Celsius. The star Rigel in the constellation Orion is a prime example. Type A, the pure white stars. These are very common stars in our view because they are quite bright. Their temperatures range from 7,500 to 10,000 degrees Celsius. Sirius, the brightest star in the night sky, is a resident of this group. Types F and G, the warm yellow friends. Type F has a slightly yellowish-white color, while Type G is the home of our Sunday. With their characteristic yellow color and temperatures of about 5,000 to 6,000 degrees Celsius, these stars have average and stable lifespans, creating ideal conditions for life to sprout on surrounding planets. Type K, the orange stars. They are a bit cooler, with temperatures from 3,500 to 5,000 degrees Celsius. We often call them the mature and calm stars. Type M, the red dwarfs. This is the most populous group of residents in the universe. They have a deep red color and low temperatures, below 3,500 degrees Celsius. Although not brilliant, they are the longest lived. A red dwarf can burn steadily for trillions of years. The map of life. The Hertzsprung-Russell diagram. Once they had this classification table, two astronomers, Ejnar Hertzsprung and Henry Norris Russell, came up with a brilliant idea around the year 1911. They drew a diagram where one axis represented temperature, color, and the other represented the star's brightness. When the stars were plotted on this map, they didn't lie scattered randomly. The vast majority of stars fell along a curving diagonal line that we call the main sequence. This is the youthful stage of a star's life, when it is busy burning hydrogen in its core. By looking at this diagram, scientists can tell what stage of life a star is in. If a star leaves the main sequence and moves upward, it is becoming a giant or supergiant star. Its outer shell expands and cools, but its large surface area keeps it extremely bright. If it falls to the bottom, it might be a white dwarf, the tiny, hot, and dense corpse left behind after a star like our Sun has died. The meaning of diversity. Now, relax your body and feel the magic of this arrangement. Classification is not just for naming things. It helps us understand the evolutionary process of the entire universe. Through the spectroscope, we can see how the dark lines of elements change between a scorching hot O-type star and a cool M-type star. In extremely hot stars, the temperature is so high that atoms are stripped of their electrons, causing their fingerprints to become different. In cool stars, scientists have even found traces of molecules, more complex chemical structures that cannot exist in the scorching heat of blue stars. The distance of millions of light years cannot stop us from knowing whether a star is a short-lived giant or a persistent dwarf. Every ray of light sent from afar carries its area code: the blue of intense youth, the yellow of stable maturity, and the red of old age, or of being small but enduring. Take a deep breath and imagine you are gliding through these starry neighborhoods. You find yourself passing by the ethereal blue light of Vega, then immersing yourself in the gentle yellow glow of the Sunday. The universe is not just a black void. It is a vibrant community where every entity has its own place and role. The diversity of stars reminds us that, even in the infinite expanse, nature always operates according to orderly and beautiful laws. We can classify, we can understand, and we can feel the connection between ourselves and those distant residents. The atoms within you were perhaps once born inside a giant O-type star, then journeyed through space to gather on this planet, under the light of a gentle G-type star. We have taken a broad look at the community of stars in the universe. But there is one special resident, our closest neighbor, whom we need to understand more than any other. That is none other than the Sun, the star that brings us warmth and life every day. How does the science of spectroscopy help us unlock the deepest secrets of this neighbor of ours? In the following chapter, we will dedicate our time to exploring the Sun's very heart. We'll see that even a star, as familiar as this one, holds astonishing secrets that only light can reveal. Now, let your thoughts drift along with the letters O, B, A, F, G, K, M, like gentle musical notes. Feel a sense of peace, knowing that every star in the sky has been understood and cherished. You are resting beneath the protection of a vast and orderly network of light. Chapter 15. The Secrets of the Sun, our nearest star. Imagine you are lying on a deserted beach on a crisp early morning. As the first rays of sunlight touch your skin, you feel a gentle, caressing warmth. That warmth has had to travel across approximately 150 million kilometers of cold space to reach you. To us, the sun is the source of life, the symbol of the day. But through the eyes of an astronomer, the sun is a gigantic physics laboratory, the only star whose surface we can scrutinize in the finest detail. Thanks to this close proximity, the sun has taught us most of what we know about the other stars in the universe. While distant stars are just faint smudges in a spectrograph, the sun sends us a brilliant and complete encyclopedia. The photosphere, the sun's radiant face. When you look at the sun through protective filters, of course, what you're seeing is the photosphere. This is the surface layer from which light can escape and travel into space. The photosphere is not a solid surface like the Earth's ground, but a sea of blazing hot gas with a temperature of about 5,500 degrees Celsius. If scientists use an extremely powerful telescope, they can see that this surface is not smooth at all. It looks like a pot of simmering soup with millions of tiny granules. Each of these granules is actually a massive column of hot gas, about 1,000 kilometers wide, rising from the depths, releasing energy into space, then cooling and sinking back down. Imagine the entire surface of the sun as a constant dance of matter and energy, a symphony of silent but intense vibrations. Sunspots, the mysterious moles. Sometimes, dark blemishes that we call sunspots appear on this radiant face. Don't let the name dark fool you. These spots are still very hot and bright, but because they are about 1,500 degrees Celsius cooler than the surrounding areas, they appear as dark patches when viewed through a filter. Through the spectroscope, scientists have uncovered a groundbreaking secret about these sunspots. Thanks to the Zeeman effect, a phenomenon where spectral lines split into two or three in the presence of a magnetic field, we know that sunspots are where the sun's magnetic field is most intensely concentrated. They are like enormous knots that block the flow of heat from below. It is from these magnetic knots that terrifying solar storms can erupt, launching billions of tons of charged particles into space, creating the beautiful aurora on our Earth. The corona, the mystical crown. One of the sun's greatest mysteries lies in its outermost atmosphere, called the corona. Normally, the corona is obscured by the dazzling light of the photosphere, and we can only see it as a faint, white halo surrounding the moon during a total solar eclipse. The strange thing is, while the sun's surface is only about 5,500 degrees Celsius, the corona's temperature reaches over 1 million degrees Celsius. This is like standing far away from a bonfire and feeling hotter than when you were right next to it. Thanks to spectrographs mounted on spacecraft like SOHO, the Solar and Heliospheric Observatory, or the Parker Solar Probe, we have analyzed the light from the corona to understand this temperature paradox. Scientists believe that vibrating magnetic waves transfer energy upward, heating this tenuous atmosphere to such incredible temperatures. Missions to touch the sun. To better understand the sun's chemical composition, humanity has continuously sent out courageous emissaries. NASA's Parker Solar Probe, launched in 2018, is the first man-made object to touch the sun's corona. With a heat shield capable of withstanding thousands of degrees Celsius, it has flown through the scorching solar winds to collect data directly. This data, when combined with the spectral lines obtained from ground-based observatories, has once again confirmed what Cecilia Payne discovered. The sun is primarily made of hydrogen, about 73% of its mass, and helium, about 25%. The small remainder consists of heavier elements like oxygen, carbon, neon, and iron. Although they make up only a tiny fraction, these impurities are the key that helps scientists understand the sun's evolution and age. A generous heart. Take a deep breath and feel the reassurance of knowing that our nearest star is an incredibly stable one. The sun is middle-aged, about 4.6 billion years old, and it will continue to shine steadily for at least another 5 billion years. It is not too hot to incinerate us in an instant, nor too cold to turn the Earth into a block of permanent ice. Sunlight brings not only life, but also knowledge. Every ray of sunlight that falls on your porch tonight, having been stored from the day, carries the imprint of nuclear reactions in the core and complex magnetic fields in the corona. We understand the vast universe largely because we have learned to understand this neighbor of ours. The distance of 150 million kilometers now feels just right, far enough for us to be safe, yet close enough for us to touch it with our intellect and with light. As you lie here, imagine the sun as a gentle mother who, despite having gone to sleep on the other side of the planet, her warmth and energy are still silently nurturing all life, waiting to awaken you tomorrow morning. The universe is vast, and our sun is just one tiny star among billions of others. But to us, it is unique, our most steadfast anchor in the infinite expanse of space. The secrets it reveals through the spectroscope are the very first bricks that have helped us build the great castle of our cosmic knowledge. Relax your hands and let your mind drift along the white, silken ribbons of the corona. You are in a perfectly functioning system, where every particle of light has a purpose, and every vibration carries a profound meaning. Chapter 16. Islands of Light. Imagine you are soaring upward, through the Earth's blanket of clouds, past the gentle yellow light of the sun, and into the pitch black of space. As you look back, our solar system becomes just a tiny speck of light. And then, as you look farther out, you begin to see fantastical shapes appearing in the darkness. These are not single stars, but billions, hundreds of billions of stars gathered together, forming enormous structures that we call galaxies. In the vast universe, galaxies are like lonely islands of light, separated by millions of light years. The nearest major galaxy to us, Andromeda, is about 2.5 million light years from Earth. This means the light astronomers see from that galaxy today began its journey when our human species had not yet truly emerged on this planet. How do we read an entire galaxy? When we observe a single star, the spectroscope shows us the sharp, dark lines of individual elements. But when we point our telescopes toward a distant galaxy, the light we receive is a blend from billions of different stars. Imagine each star in that galaxy is like a musician in a colossal symphony orchestra. The hot, blue stars play the high, powerful notes. The yellow stars, like our sun, play the steady, central melodies. The old red stars provide the deep, resonant bass notes. From a great distance, we cannot hear each individual musician, but only the overall harmony. Scientists call this an integrated spectrum. Discovery. By using great telescopes like Hubble or James Webb, humanity has collected this blended light and begun to dissect it. Though mixed together, the chemical fingerprints of the elements are not lost. They just become fainter or a bit wider. Through this symphony of light, we can determine what types of stars the galaxy is primarily made of, how old it is, and how rich in metals it is. Young galaxies and old galaxies. In the language of astronomy, metals are not just iron or copper, but all elements heavier than hydrogen and helium. As we learned in Chapter 9, these elements are forged only in the hearts of stars. Therefore, by measuring the amount of heavy elements in a galaxy, we can tell how many generations of stars it has experienced. Blue spiral galaxies. Like our own Milky Way or the Andromeda galaxy, they often display a brilliant blue hue in their spiral arms. Their spectra reveal the presence of abundant, fresh hydrogen gas and the formation of young stars. These are vibrant islands of light, where the cosmic forges are still working tirelessly. Red, elliptical galaxies. In contrast, there are galaxies that look like hazy, orange-yellow or red globes. When analyzing their light, scientists find that they have almost no gas left to create new stars. They contain only old, cooling stars. These are like the retirement homes of the universe, where the remnants of previous stellar generations are slowly fading away. A window to the past. The most miraculous thing about studying distant galaxies is the ability to look back in time. Thanks to the expansion of the universe and the redshift phenomenon discovered by Edwin Hubble, we can observe galaxies at the very edge of the observable universe. When the James Webb Space Telescope points toward the faintest specks of light, it is capturing photons that have traveled for 13 billion years. Analyzing the spectra of these primordial galaxies reveals a fascinating truth. They contain very few heavy elements. They are almost entirely pure hydrogen and helium. This aligns perfectly with the Big Bang theory, showing that the early universe was very simple, and complex chemical elements were gradually built up over time, interacting islands. Not all galaxies drift peacefully. Sometimes, due to the immense pull of gravity, two giant islands of light can collide and merge. Our own Milky Way and the Andromeda Galaxy are currently approaching each other at a speed of about 110 kilometers per second. In about 4 billion years, these two islands will begin a grand cosmic dance of collision to form a new, more massive galaxy. Thanks to the spectroscope, we can see the chemical disturbances in colliding galaxies. The pressure from the collision compresses gas clouds, triggering the simultaneous birth of millions of new stars, creating vibrant and energetic spectra. The silence amidst a sea of stars. Take a slow breath and feel the overwhelming yet orderly vastness of the universe. Each distant galaxy, though appearing as just a faint smudge on a photographic plate, is in fact a world containing countless wonders. There are billions of solar systems, possibly millions of planets, and perhaps there are also beings looking back towards us, wondering about the chemical composition of the Milky Way. We, tiny creatures living on a planet orbiting an ordinary star, are able to comprehend the nature of enormous entities millions and millions of kilometers away. This is thanks to the persistence of human intellect and the faithfulness of light. Light never lies. It carries the identity of an entire galaxy to tell us the history of space. The distance of millions of light years is no longer a separating wall, but an open corridor through time. Every time we decode the spectrum of a galaxy, we add another page to the chronicle of the cosmos. Let your mind drift among the swirls of the galaxies. Imagine yourself standing in the middle of a vast space, surrounded by shimmering, ethereal islands of light. You feel so small, yet so grand, for being a part of this magnificent whole. The night sky is not just a black curtain. It is an ocean full of beckoning islands, and we have learned how to build vessels of light to explore those distant shores. Chapter 17. Searching for life in the breath of alien planets. Imagine you are standing in a vast field under a silent night sky. In the distance, a small star glitters like a grain of golden sand. Around that star, tiny planets may be quietly orbiting, like the Earth's siblings in our solar system. These planets do not emit their own light. They hide in the encompassing darkness of the universe. For thousands of years, humans could only dream of them. But today, thanks to the magic of spectroscopy, we can not only find them, but also begin to sniff out the scent of their atmospheres. As of the year 2026, scientists have discovered over 5,500 exoplanets. But finding a new planet is just the beginning. What we truly desire is to know if there is air to breathe, water to drink, or any traces of life. The transit, a fleeting moment of light. How can we see the atmosphere of a planet tens of light years away? Astronomers use an incredibly subtle technique called transit spectroscopy. Imagine a brilliant star is a giant lantern. As a planet orbits that star, it will sometimes pass directly in front of the star from our perspective on Earth. This phenomenon is called a transit. When this happens, the planet will block a small fraction of the star's light. But something magical occurs. A portion of the starlight is not completely blocked, but instead passes through the thin atmospheric layer surrounding the planet before reaching our telescopes. This atmospheric layer acts like a color filter. As the light passes through the planet's breath, gas molecules there absorb very specific colors, leaving characteristic dark lines in the star's spectrum. By comparing the star's spectrum during a transit to its normal spectrum, scientists can isolate the fingerprint of the planet's atmosphere. Biosignatures, the breath of life. In the cosmic laboratory, each type of gas has its own unique voice. When scientists look at the spectral lines collected by telescopes like James Webb, they are fervently searching for biosignatures. Water vapor. This is a prerequisite for life as we know it. If we see traces of water vapor, we know the planet has clouds, rain, and possibly vast oceans, carbon dioxide and methane. The simultaneous presence of these two gases is an extremely important sign. On a rocky planet, if they appear together, it could be evidence of geological activity or even the biological processes of microorganisms. Oxygen and ozone. These are the most powerful signatures. On Earth, most oxygen is produced through photosynthesis by plants. If we were to find a planet with an oxygen-rich atmosphere, it would be one of the greatest discoveries in human history. In the year 2023, the James Webb Space Telescope made waves by analyzing the atmosphere of the planet K2-18b, a planet located about 120 light-years from us. The spectroscope found traces of methane and carbon dioxide, and even hints of a molecule called dimethyl sulfide. On Earth, this molecule is produced only by life, specifically by phytoplankton in the oceans. Although more research is needed for confirmation, this has ignited a powerful hope for distant ocean worlds. The TRAPPIST-1 system. 7 rocky siblings. One of the most exciting targets is the TRAPPIST-1 system, located about 40 light-years away. There, 7 Earth-sized planets orbit a cool red dwarf star. 3 of these 7 planets lie within the habitable zone, where the temperature is just right for liquid water to exist on the surface. Let your imagination run wild. Picture yourself standing on the surface of the planet TRAPPIST-1e. The sky there isn't blue like ours, but might have a soft red or orange hue from the light of its parent star. When you look up, you might see the other sibling planets appearing as large as moons. Thanks to spectroscopy, we are peeling back the atmospheric layers of each of these planets one by one to see if any of them harbor the warmth of life. The patience of world hunters. Collecting light from a planet's atmosphere is a task that demands extraordinary patience. The light passing through the thin and faint planetary atmosphere is incredibly weak, accounting for only 1/10,000th of the star's brightness. To obtain a clear spectrum, the James Webb Space Telescope must observe the planet transit multiple times, accumulating every single photon over many hours. Organizations like NASA and ESA are not stopping at James Webb. In the near future, missions like the European Space Agency's Ariel will be launched with the specific task of analyzing the atmospheres of thousands of different planets. We are creating a chemical map of the galaxy to find out if Earth is a unique gem or just one of billions of other warm homes. The connection between the stars. Take a deep breath and feel the miracle of your own breathing. The oxygen nourishing your body every second is the result of a grand chemical process on this planet. When we look at the spectrum of a distant planet and see the signature of oxygen, we are seeing a form of biological kin. A distance of trillions of kilometers suddenly feels remarkably close. The universe is no longer a cold and empty place. It is teeming with possibilities, with the potential for life to blossom. Light has become a bridge, carrying the breath of distant worlds right into our laboratories. Let your shoulders relax, and let your mind be soothed by the thought that we are not alone. Though we cannot yet fly there, with our intellect and our love for the stars, we have already touched the skies of other planets, felt the winds and the moisture of worlds that have yet to be named. The stillness of the night is the perfect time for us to contemplate our place in the cosmos. We are part of a ceaseless flow of matter and energy. The chemical elements that create life within you are the very same elements we are searching for in the farthest reaches of space. In the next chapter, we will learn about the greatest eye that humanity has ever sent into space to carry out these missions. We will explore the James Webb Telescope, a masterpiece of technology that helps us peer through the mists of time to see the very first light of the universe. For now, let the breath of that distant planet merge with your dreams. Imagine billowing clouds of water vapor and deep blue oceans awaiting us somewhere out there. You are safe, enveloped in the understanding and wonder of a universe teeming with life. Chapter 18. James Webb, the eye that sees through time. Imagine you are holding a miraculous pair of binoculars. These binoculars don't look at what's happening right in front of you, but have the ability to see through thick walls of cosmic dust, to peer across trillions of kilometers of space, to observe events that happened 13 billion years ago. Those binoculars are called the James Webb Space Telescope, the grandest project humanity has ever undertaken in a collaboration between NASA, the European Space Agency, ESA, and the Canadian Space Agency. The James Webb Telescope is unlike any telescope you have ever seen on the ground, or even its famous predecessor, the Hubble. It is a work of art in technology and physics, launched into space on December 25, 2021. Since then, it has become humanity's sharpest eye, opening a new era in deciphering the code of the universe. The golden blossom in the darkness. The most striking image of James Webb is its enormous mirror. Instead of a single, round mirror, James Webb possesses 18 hexagonal segments fitted together, resembling a brilliant golden blossom blooming in the night. This entire mirror has a diameter of up to 6.5 meters, much larger than Hubble's. What is special is that the surface of these 18 mirrors is coated with an extremely thin layer of gold. Do you know why scientists chose gold? It wasn't for decoration, but because gold is the best material for reflecting infrared light. James Webb doesn't see the universe in visible light that the human eye can perceive. It sees the universe through infrared rays, also known as heat radiation. Relax your mind and imagine the world around you through an infrared lens. Cold things would disappear, and warm things would appear brilliantly. In the universe, newly forming stars are often hidden behind dense clouds of dust. Normal light is blocked by this dust, but infrared light is not. It passes through the dust as if it were completely transparent. Thanks to this, James Webb can see into the nurseries of stars, where the lives of new suns are just beginning to sprout. The journey to a point of cosmic balance. In order to detect the faint heat signals from the very edge of the universe, James Webb needs an extremely cold environment. If it were too close to Earth, the heat from our planet and the sun would blind it. Therefore, scientists sent it to a special location called the second Lagrange point, located about 1,500,000 kilometers from Earth. This is a point of gravitational equilibrium, where the telescope can maintain its position relative to the Earth as they both orbit the Sunday. To protect itself from heat, James Webb carries a massive 5-layer sun shield, each layer as thin as plastic wrap, but as large as a tennis court. This shield blocks all light and heat from the sun, keeping the scientific instruments at a temperature of -233 degrees Celsius colder than any natural place on Earth. The spectrometer, the heart of the all-seeing eye. Although the breathtaking images James Webb sends back have astonished the world, for scientists, the real treasure lies in the spectrometers installed inside it. James Webb carries incredibly sophisticated spectroscopic instruments like NIRSpec, near-infrared spectrograph, and MIRI, mid-infrared instrument. These instruments allow James Webb to perform its two greatest missions. Looking at the first light. Due to the expansion of the universe, which we explored in Chapter 12, the light from the first stars and galaxies born after the Big Bang has been stretched so much that it is no longer visible light, but has become infrared. Only James Webb is sensitive enough to capture these photons that have traveled for 13.5 billion years and analyze their chemical composition. It is telling us how the early universe cooked the first elements, analyzing the breath of alien planets. As mentioned in the previous chapter, James Webb can analyze the light passing through the atmospheres of exoplanets with unprecedented precision. It can resolve extremely faint spectral lines to search for water, carbon dioxide, and even complex biosignatures, helping us answer the question of whether we are alone in this universe. Discoveries that are changing textbooks. In just a short time of operation, James Webb has sent back data that has overturned many old theories. It found ancient galaxies that were far too large and developed for what we thought was possible so soon after the Big Bang. It captured vivid details inside the Eagle Nebula, showing that the pillars of creation are not inert blocks of dust, but dynamic, cosmic forges. Every time James Webb points its lens at a dark patch of sky where we previously thought there was nothing, it discovers thousands of new galaxies glittering like diamonds. It shows us that the universe is richer and more magnificent than we could ever imagine. The solitude of a lone warrior. Imagine the lonely yet proud existence of James Webb. 1,500,000 kilometers away from us, it works silently in the bone-chilling cold and darkness. There is no one there to repair it if it breaks. Everything had to work perfectly the first time. This is the result of decades of labor, of the perseverance of thousands of the most brilliant minds on our planet. James Webb is not just a telescope, it is the embodiment of humanity's thirst for understanding. It proves that even though we are tiny beings on a small blue planet, we have the intellect to reach the very ends of space and time in our search for truth. The distance of millions of light years is now just a number, because James Webb has brought the images and information from there directly to us. Thanks to it, the coded message of light that we have diligently studied in the past chapters is being deciphered faster than ever before. Breathe steadily, slowly. You are living in a wondrous era where the greatest secrets of the universe are gradually being unveiled. Feel the sense of peace that comes from knowing we have an all-seeing eye, protecting and guiding our knowledge in the vast cosmos. James Webb is still tirelessly observing, receiving faint infrared rays to weave a panoramic tapestry of our history. And as you close your eyes to fall asleep, remember that somewhere far out there, humanity's golden blossom is still in full bloom, illuminating the darkest corners of the past. Chapter 19: Phantoms in the Darkness. Imagine you are at a magnificent masquerade ball in an ancient castle. You see dancers in sparkling gowns spinning to the rhythm of a symphony. But as you look closer, you notice something strange. The dancers are not moving on their own. They seem to be lifted, pulled, and led by invisible partners. You cannot see these partners, but from the way the dancers twirl and the speed at which they move, you know for certain that a hidden force is present in the room. Our universe is just like that ballroom. Everything we have discussed so far, the brilliant stars, the solid rocky planets, the vast clouds of hydrogen gas, and even the distant galaxies, actually makes up an incredibly small fraction of reality. Scientists were stunned to realize that all of this luminous matter accounts for only about 5% of the total mass and energy of the entire universe. So, what is the other 95%? They are the phantoms we call dark matter and dark energy. Dark matter, the invisible glue of galaxies. The mystery of dark matter began to emerge in the 1930s, thanks to the work of astronomer Fritz Zwicky, and was later strongly reinforced by Vera Rubin in the 1970s. As she observed the movement of stars at the edges of spiral galaxies, she noticed something impossible. The stars on the outskirts were moving just as fast as the stars near the center. According to the normal laws of physics, if only the matter we can see existed, the distant stars at the edge should have been flung out of the galaxy long ago, because the gravitational pull wouldn't be strong enough to hold them. This proved that there must be something incredibly heavy, incredibly massive, but which emits no light or heat, enveloping the galaxy and keeping everything from flying apart. Scientists call it dark matter. It doesn't reflect light, absorb light, or emit light. Our messenger, light, is completely powerless against it. Dark matter makes up about 27% of the universe. It acts as a gigantic cosmic skeleton, an invisible glue that helps form the large-scale structures of the universe, allowing galaxies to gather together. Although we can't see dark matter directly with a spectroscope, we can see its footprints through a fascinating phenomenon called gravitational lensing. Imagine a huge clump of dark matter sitting between Earth and a distant galaxy. The immense mass of the dark matter will bend the space around it, causing the light from the galaxy behind it to be bent as it passes by, just like light passing through a thick glass lens. By looking at those distorted images of galaxies, scientists can map out the hidden regions of dark matter. Dark energy, the force pushing everything away. If dark matter is what pulls everything together, then there is another ghost, far more powerful and mysterious, that is doing the opposite. That is dark energy. In the late 1990s, while analyzing the light from very distant supernova explosions, astronomers discovered a shocking truth. The universe is not just expanding as Edwin Hubble had found, but it's expanding faster and faster. Some mysterious repulsive force is counteracting gravity, constantly stretching space and pushing galaxies away from each other at a dizzying speed. Dark energy makes up about **68% of the universe. It isn't concentrated in one place like dark matter, but seems to be present everywhere, in every cubic centimeter of empty space. We still don't know what dark energy truly is, but we see its effects through the redshift of light. As space is stretched faster, the light from distant galaxies is stretched more than ever before it reaches us. We are tiny miracles. Relax your body and think about this for a moment. You, me, this house, and even that brilliant sun are all made of ordinary matter. The kind of matter that interacts with light, that shines, and that tells stories through a spectroscope. We are entities belonging to that rare 5%. We are like sparkling sea foam on the crest of a dark and deep ocean. The existence of dark matter and dark energy shows that the universe holds so much that human intellect has yet to reach. However, it is precisely by understanding light that we have realized the existence of darkness. Light has led us to the very edge of our understanding, showing us that behind that curtain of night is a network of great forces at work. The millions of light years of distance are now not only filled with stars, but also with invisible phantoms shaping the future of all space. Thanks to dark matter, galaxies could form to have stars, and thanks to stars, we have the chemical elements to create life. Everything is intricately connected in a profoundly subtle way. Take a steady, gentle breath. Feel how special it is to be made of matter that can shine. You carry within you the light of the stars, and your intellect can perceive even the most invisible things in the universe. The darkness out there is not something to fear. It is part of the great cosmic home we inhabit. Now, let your mind relax completely. Imagine the universe as a mysterious black silk cloth where galaxies are pearls, and dark matter is the invisible thread that binds them together. You are floating in the protection of eternal laws. There is nothing to rush, nothing to worry about, because the entire universe, both its light and dark parts, is operating in a rhythmic and peaceful harmony. In the final chapter of this journey, we will return to ourselves. Together, we will contemplate the deepest connection of all. Why are we called stardust? And how does this entire journey of deciphering light lead us back to the human heart? But for now, let the gentle phantoms of the universe guide you into a deep sleep. Feel the tranquility and vastness of space embracing you in the soft arms of the night. Hello. Together we have traveled a long journey through space and time. from Newton's small rays of light to the great eyes of the James Webb. Tonight, let your body completely relax, your breath slow and deep. This is the final chapter in our symphony, where all the distant stars and your heart become one. I invite you to listen to Chapter 20. Chapter 20. We are stardust. Imagine you are lying on a lush green lawn in the absolute silence of a moonless night. You look up at the sky, where millions of points of light are twinkling. After the past 19 chapters, perhaps now when you look up, you no longer see them as anonymous specks of light. You see balls of burning hydrogen, metallurgical forges tirelessly crafting matter, and messengers of light carrying colorful secret letters toward Earth. But there is one final secret, the most beautiful and profound of all, that spectroscopy has revealed to us. The universe is not just out there. The universe is right inside your own body. The connection from the forges of stars. Gently place your hand on your left chest, feeling the steady beat of your heart. In the blood flowing through your heart is iron, the element that helps red blood cells carry oxygen to nourish your body. Where did that iron come from? It was not naturally created on Earth. As we learned in Chapter 9, that iron could only be forged inside the cores of massive stars in the final moments of their lives before they exploded into a glorious supernova. Take a deep breath. The oxygen filling your lungs, along with the carbon that makes up every cell and the calcium in your skeleton, were all once needed in the hundreds of millions of degrees heat of stars that died billions of years ago. When those stars ended their life cycles, they scattered these precious elements into space. That dust drifted, gathered, and formed the sun, the earth, and ultimately, you. We are the universe's way of knowing itself. The astronomer Carl Sagan famously said, "We are made of star stuff." This is not just a romantic saying, but a pure scientific fact, proven by the spectral lines we have studied. When you use a spectroscope to look at a star 1 million light-years away and see the line for magnesium, you are seeing the same type of atom that is present in your muscles. When you see traces of hydrogen in a distant galaxy, you are seeing the siblings of the hydrogen atoms in the water molecules that make up your body. The miracle is this: the universe took 13.8 billion years to evolve, to forge matter, to create the complex human brain. And now, those very atoms that were once in the heart of a star are using that intellect to look back at the sky and understand their own origin. We are the eyes and the brain of the universe, the means by which the cosmos observes and feels its own beauty. Light is a reminder of immortality. Whenever you feel small before the vastness of space, remember that you carry within you the legacy of an entire galaxy. The atoms in your body have existed since the dawn of time, have traveled through millions of kilometers of cold space, have survived cataclysmic explosions to be here, right at this moment. The light that we have learned to decipher is the bridge that erases all distance. It shows that there is no separation between us and the universe. We are not strange visitors on this planet. We are the children of the stars, carrying in our veins blood forged from light and extreme heat. Closing the journey, opening to peace. Our 20-chapter journey comes to a close here. We have gone from the simplest things, like a ray of light passing through a prism, to the mysteries of dark matter and the breath of alien planets. We have learned how to read the chemical composition of the most distant entities without ever leaving the ground. But more important than the knowledge, I hope this journey brings you a deep sense of peace. The universe is vast and majestic, but it is also orderly and full of grace. Every law of physics, every spectral line of color, is telling a story of unity and persistence. Tonight, when you close your eyes, imagine yourself lying amidst a sea of sparkling stars. You no longer feel fear of the darkness or the vastness. You know that every star out there is a part of you, and you are a part of them. You are breathing in sync with the universe. drifting on the current of time. Relax your hands and let your mind be completely at ease. The worries of daily life are just tiny specks of dust before the eternity of light. You are stardust, and stardust never disappears. It only transforms from one form to another in the endless symphony of life. I wish you a very good, deep sleep. May your dreams be colored with the blue of Sirius, the yellow of the sun, and the warm red of distant galaxies. You are home in the benevolent embrace of the universe. Tạm biệt bạn, người bạn yêu, những vì sao. Hẹn gặp lại bạn trong những hành trình khám phá tiếp theo của tâm trí. Còn bây giờ, hãy để ánh sáng của 13,8 tỷ năm vỗ về giấc ngủ của bạn.